Hi, this is Calandra. In this video, we'll discuss the meaning of domain and range. First, we'll look at determining the domain and range from a relation or from a graph. The set of all possible input values of a function is called its domain. The input values of a function are typically represented by the variable x. The set of all possible output values of a function is called its range. And the output values are typically represented by the variable y. So in this example, we want to find the domain and range of the following functions. So our first function is a relation, a set of ordered pairs. So we're going to be able to list all of the elements in our domain because we see there's a finite number of them. So we can use set notation, and I see all of my possible x values are 9, 2, 0, and -5. And that's it. My range is a set of all y values represented for my function. So I see my y values, which is the second coordinate, are 4, 3. I have another 3, but you don't need to list a number more than once in a set. It's already accounted for. And 1. And that would be the range of that function. Going on to our second example. So now we have a graph, and we want to describe all of the x values that have a corresponding point on this graph. So you want to be careful when doing this. Make sure you're looking at your x-axis. And the way that you can think about it is, okay, what x value do I pick that has a corresponding point on the graph? So if we move to the right, notice any x value that we pick is going to have a graph. Even if I go further out to the right, since my graph has the arrows indicating that it will continuously extend down and to the right, that means any x value that we pick will have a corresponding point on the graph. You can do a similar examination going to the left. Any x you pick, there's a point on the graph. Any x, there's a point. So in this case, the domain is going to be the set of all real numbers because any x value that we pick has a corresponding point on the graph. So we can denote all real numbers in interval notation from -infinity to +infinity. So we could not list the numbers like we did in our first example because there are infinitely many. So we can't use set notation, we have to use interval notation. Okay, now let's look at the range. Okay, the range are all possible y values. So now we want to make sure that we're looking along the y-axis. So with our intervals, we want to start with the smallest number first. So if I look at this this y value of -10, I see there will be corresponding points on the graph. If I go even lower, down to -20, eventually my graph is going to reach that point and continue to go down. So since we do not have a smallest y value, we'll start with -infinity, always a parenthesis because nothing can equal -infinity. And then as I move up my y-axis, I see that all of these y values have a corresponding point on the graph until I get to a y value of 7. As soon as I go higher than 7, there are no longer points on my graph that correspond to that y value. So the range will go up to 7. It includes 7, so we draw a bracket, and that's our answer. Okay, looking at our third graph. Okay, let's start with our domain again. So the domain is the set of all x values. So we're now looking at our x-axis. So let's start with the smallest x value. I see that I have an arrow going to the left, so that means the graph is going to continue in that pattern to the left. So any x value that I pick will have a point on the graph until I get to an x value of -2. At -2, we see that we have an open circle. An open circle means that it's not included on the graph. The reason why that open circle is helpful is that means we have every single point on the graph until we get to -2. So that lets you denote, for example, -2.1, -2.001, -2.00001. All of those numbers are included, but as soon as we get to -2, that point is not part of the domain. So to denote that part of our interval, our x's can be any negative number until we get to the value of 2. Since 2 is not included, we draw a parenthesis, -2. As soon as we go to the right of -2, we have points again. So that means we're going to need to start another interval. So we're going to draw a union sign in between all of our disjoint intervals. So starting with -2. And again, I have an x value for all of these numbers until I get to 3. 3 is also included because I have a closed circle there. So closed circle means included. And then as soon as I go to the right of 3, notice that my graph jumps up to this portion up here. But there is no gap in my x values because we have that closed circle. So my domain would be from -2 with a parenthesis to infinity. Okay, so those two intervals together make up our domain. Okay, well now let's look at our range. So we want to start with the smallest y value that's represented on our graph. So we're looking at our vertical axis. So the smallest y value is at 3. And we see that 3 actually does have points on our graph when y equals 3. So that means that with my interval, I'm going to start with a bracket at 3. Okay, so we have a y value of 3. If I go above 3, I see that I still have points on my graph, and I have corresponding y values until I get to 5. We have a closed circle when y equals 5, so that means it's included, so I end that with a bracket. As soon as I go higher than 5, I don't have any points on my graph, so I need to leave that interval out. But when I get to 7, it looks like I'm going to have points again on my graph. However, since there's an open circle, 7 is not included. So we're going to have to do an open parenthesis at 7, but then any y value bigger than 7 will have a corresponding point. So we'll have 7 to positive infinity. Okay, going to our last graph. This is the graph of a rational function. And with rational functions, you have something called asymptotes, which are lines that are not part of your graph, but that your graph gets infinitely close to. And those asymptotes are denoted with dotted lines. Okay, so the red represents the graph of our function. So we want to be able to tell what are all of the x values represented on that red function. So we're still going to examine it the same way. Looking at my x values starting in the negative direction, I see that all of these x values have a corresponding point on the graph until I get to an x value of 2. This graph gets closer and closer to that asymptote at 2, but it never crosses it. So that means that that first interval for my domain will be from negative infinity until I get to 2, and 2 is not included, so we do a parenthesis. As soon as I go to the right of 2, I see I have points on my graph again up in the first quadrant, and then the graph will continue to go to the right. So the second part of that interval will be from 2 with a parenthesis to infinity. Okay, for the range, we want to look at our y values. So starting with the smallest y value, since this function continues to go down, that means any y value that we pick will have a corresponding point on the graph. So my y's will start at negative infinity, and I have a corresponding point on the graph for all of the y values until I get to a y value of 4. Since there's an asymptote there and my graph does not cross the asymptote, that means that's where this interval will end. It never has a y value of 4, so we do a parenthesis there. As soon as we go bigger than 4, there are points on the graph again that continue up to infinity. So that last interval would be from 4 to positive infinity.